Let us have a look into another technology to understand the subsurface, which is known as surface nuclear magnetic resonance, right, SNMR, right. It is as usual a non-intrusive technique, especially for near surface investigation. Usually this method is suitable to investigate up to 100 or maximum of 150 meters given the suitable subsurface conditions, right. So, this method is ideally suited for near surface investigation. This method is also called as simply nuclear magnetic resonance or magnetic resonance imaging, magnetic resonance sounding or proton magnetic resonance. These are all some of the names given to this method. Popularly, it is known as surface nuclear magnetic resonance, and most of us are familiar with the MRI, right. There are many hospitals as well as centers, scanning centers, right, take the MRI images of human body, especially to understand the problem with regard to the tissues, right, spinal cord issues, people with back pain, they are advised to chronic back pain, they are advised to go for such investigations, right. The same technology is also used to understand the subsurface since last 25-30 years, right. One of the greatest advantage of this method is this is the only, perhaps this is the only geophysical method that directly estimate the volume and spatial distribution of fluids, right. That means beneath the surface of the earth, we are able to directly determine the volume of fluids. How? By recording the resonance signals from the protons, right, from the proton containing fluids, right. We are making use of the protons in the fluids to understand about the volume of fluid that is present below the surface of the earth, right. When we talk about fluids, protons are present in water as well as hydrocarbon, right, beneath the surface of the earth. So, here is a method that help us to directly understand what is the volume of fluid that is present below the surface of the earth, right. Once if you can estimate the volume of fluid, that directly gives us information about the porosity. Porosity is the ratio of volume of voids to the total volume, right. Once if you are estimating the volume of fluids, that is nothing but the porosity of the formation. In the upper zone where the formation is not saturated, right, that help us to understand the moisture content. So, when does it give the porosity? In the saturated zone, volume of water is equivalent to porosity, whereas in the unsaturated zone, above the water table, we are able to estimate the volume of moisture present in the vadose zone, right. That means the subsurface is divided into two zones, vadose then saturated, right. NMR directly estimates the porosity of the saturated zone, because volume of voids is nothing but volume of water is indicating the volume of pores. Whereas in the vadose zone is partly saturated with water as well as air. So, volume of water present in the vadose zone can be also estimated. We can also indirectly assess the pore size distribution, right, depending upon the volume of pores or depending upon the volume of water or fluid present below the surface of the earth, we can also indirectly arrive at the pore size distribution, right. And here is an example wherein this company has estimated the water content below the surface of the earth. Water content has also been extrapolated to understand the porosity as well as the hydraulic conductivity. That means, once if you are able to arrive at the porosity, there are several empirical relations that are available to convert porosity into hydraulic conductivity. Hydraulic conductivity is the property of the formation to transmit, how easily it can transmit water. So, hydraulic conductivity of a formation is its ability to transmit water. So, from porosity we can estimate the hydraulic conductivity indirectly using some empirical relationships. So, that is the advantage of surface nuclear magnetic resonance. This method was initially used, right, mainly to focus on understand the presence of oil, that is hydrocarbon, below the surface of the earth. So, initially the method evolved to understand the presence of hydrocarbon below the surface of the earth in the form of logging method, which we are going to see under geophysical logging. Right, in geophysical logging, one of the logging method is the same, nuclear magnetic resonance. So, here we call it as surface nuclear magnetic resonance, over there it is called as borehole nuclear magnetic resonance logging, right. However, though it was initially used for hydrocarbon exploration, today it is very widely used in understanding the hydrogeology, especially to understand the groundwater conditions below the surface of the earth, and also in environmental investigations, right. So, this is in brief a kind of an introduction about the surface nuclear magnetic resonance. So, here is the theory behind the surface nuclear magnetic resonance. It is not really surface. Here you will understand the fundamentals of nuclear magnetic resonance or magnetic resonance imaging. Let us carefully look into this video, right. So, here any matter is made up of atoms, as you see in this video, and some of the atoms, especially fluids, has got hydrogen, right, especially fluids has got hydrogen. If you put all the atoms under the magnetic field, so here you can see a magnetic field. So, this magnetic field, once if it is put, when this matter is put under the magnetic field, so it is able to align itself parallel to the magnetic field. In that situation, we are bringing in an oscillating magnetic field, as you see here. This oscillating magnetic field makes these protons to spin, as you can see in this video, right, and after spinning it tries to align in a direction perpendicular to the magnetic field that was existing here, right. After we continuously, right, put this under the external magnetic field, then suddenly we remove the magnetic field, right. So, when we remove the magnetic field, it tries to slowly realign itself to its original position, right. So, this helps us to cause some kind of a signal during the process of relaxation. From here it went back to this place. So, this relaxation time help us to understand about the subsurface in surface nuclear magnetic resonance. In MRI, we use the same technique to understand the tissues, the conditions of tissues in our body, right. So, after having seen little bit, after having understood about the theory little bit, let us look into the surface NMR, the theory behind the surface NMR, right. So, here the measurement of the signal involves 3 stages. The same thing we had seen on the previous page. First is, in the previous video, we brought in some external magnetic field, whereas when we are discussing about the earth itself is functioning like a magnet. So, what is happening due to the earth's magnetic field is protons in the fluids beneath the surface of the earth, right, are in equilibrium conditions, right, in alignment with the background magnetic field. So, what is the magnetic field here? It is the earth's magnetic field. So, earth's magnetic field, if you denote it as B0, and all the protons in the fluids align themselves parallel to the earth's magnetic field, right. In the traditional NMR techniques, for example, we were discussing about the MRI scanning performed by a scanning center or performed in a hospital. Over there, they use a strong magnetic field to align the protons in our body, to align the protons parallel to the magnetic field that is generated within the MRI instrument. Whereas, in the case of our investigation over the surface of the earth, we do not use any magnet, but we use the magnetism of the earth itself, right. So, the first stage, the protons in the fluids beneath the subsurface, right, beneath the surface of the earth, we have to cut this, right. What happens is the protons below the surface of the earth, that means where the protons are present in the fluids, these protons are in equilibrium because they are under the influence of the earth's magnetic field, right. In such a situation, we bring in, right. So, now due to the earth's magnetic field, the protons are in alignment, right, as you can see here, right. They are in alignment to the north and south pole of the earth, that is parallel to B0. In such a situation, we are bringing in something external that is going to excite or perturb the protons. So, these protons are perturbed or excited. How? By subjecting them to oscillating magnetic field. That means, with the help of a radio frequency pulses, we disturb or excite these protons, right. How are we generating this oscillating magnetic field? We make use of a transmitter coil which is kept on the surface of the earth. We are going to see, right. We keep a coil on the surface of the earth, somewhat similar to electromagnetic methods. We had in electromagnetic method also we keep a coil on the surface. Similar to that, here we keep a coil. This external field now causes a change in the alignment of magnetic moments of the protons, right. Now, these they are all aligned like this, right, parallel to the earth's magnetic field, right. The alignment of these magnetic moments, especially in fluids in the hydrogen nuclei, are going to change. That means, how they are going to change? They are going to be changed in perpendicular direction. That means, they were like this in this direction, right. They are slowly changing, right, in a direction perpendicular to the earth's magnetic field. How this was made? Because we generated some radio frequency using a oscillating magnetic field, right. This has made the protons to change its orientation, right. So, these radio frequency pulses are produced by very high voltage alternating current that are transmitted through this coil, right, at Larmor frequency, right. So, the frequency is decided based on the magnetic moments the earth is experiencing at the site of our investigation, right. So, this will make the protons to change its orientation from the Earth's magnetic field. Previously, it was aligned to the Earth's magnetic field. Upon this, right, upon our excitement, or we had given excited the protons or perturbed the protons. So, protons changed their orientation from here to here, right. This is the second stage. So, we have seen first is equilibrate, second is excitation. What is the third? Third is the measurement. So, third is the measurement. The perturbation is then stopped. That means, we had energized, we applied some radio frequency, this is going to be cut down now. So, once if you stop, then the protons will now try to relax back, right. Initially their orientation was this way. Due to radio frequency, the orientation got changed to 90 degrees, right. This is going to relax now. This causes them to emit some detectable signal as they return back to the equilibrium state. So, from here they actually spin itself, right, this way. It spins slowly, it attains the equilibrium, right. So, this is how it tries to, it is somewhere here, this one goes in a conical path, right. So, slowly it attains the position that it was occupying before the radio frequency, right. So, this relaxation involves the precision of proton about the B naught, that is, as I have drawn here, it goes it spins around, right, in a axis which is indicated by B naught here. So, it spins like this, as maybe I will redraw, right. So, it spins around this green bar, slowly it loses its kind of an energy that it gained during the application of radio frequency. So, as it spins back to its original position, this spinning creates some magnetic field. We are able to measure some magnetic field, right, and it approaches to the background over time. That means, what do I mean by background? So, initially they were, as you can see in this picture, they were like this, right. So, now it got, after while applying the radio frequency, it turned like this, it spins. So, while spinning, its level keeps on changing. As you can see in this arrow, it reaches its original condition. This spin causes some measurable amount of magnetic field. This is again measured by the same coil which we had used for generating radio frequency. To generate radio frequency, we used a coil, then we stopped the radio frequency. The same coil now measures this magnetic field, right, which is known as FID, free induction decay. Free induction decay induces a voltage within the same surface coil, right, that records the signal, right. It is known as T2, which is known as transverse relaxation time or transverse decay time. That means, how much time it takes for it to relax back to its original condition. The initial strength of T2 is proportional to the water that is present in the formation, right. So, the initial strength of T2 indicates about the presence of water below the surface. The T2 delays with the timing, right, that can be related to the size of the pores in which water resides. So, T2 is an indication of the volume of water that is present beneath the surface. So, this is the theory behind NMR. That means, to go back, already the protons are in equilibrium because of they are in the Earth's magnetic field. Now, we perturb that by applying some radio frequency. This radio frequency leads to the change in orientation of these protons. Initially, they were aligned this way, right, parallel to the B naught is the Earth's magnetic field. Now, because of our excitation, it got turned like this, right. Now, we are going to stop the radio frequency. Once the radio frequency is stopped, then they again realign. These protons realign themselves back to its original position by actually spinning around this axis. This spinning causes a measurable amount of magnetic field, which is sensed by the same transmitter coil, because transmitter is no longer transmitting, right. So, initially it transmitted, then switched off. The same transmitter coil now receive the signal, right, which is recorded. This recording, which is the transverse decay, which is T2, which indicates about the volume of water present below the surface of the earth. So, this is the theory, right. What are the important aspects of SNMR? SNMR, as we have been discussing, help us to directly understand about the porosity, right. We had already seen in saturated conditions, the measurement represents the total porosity. What measurement? We are measuring the volume of water below the surface. So, volume of water in the saturated zone directly gives us the volume of pores. So, we are able to understand about the porosity. This signal is sensitive to the presence of water. We obviously know, because protons are present in the hydrogen. Hydrogen is present only in water as well as other fluids below the surface. The other common fluid is the oil, which we are looking for, right, in oil exploration, right. And hence, the NMR signal depend on the volume of water, also on the pore surface interaction, right. The interaction of the pore surface with the surrounding fluid also is responsible for the SMR signal. The interaction between pore surface and the fluid is related to the reflexivity and size of the pore, right. What is the surface reflexivity of the sand grains or clay grains, and what is their size? All of them control the SNMR signal. Thus, the greatest advantage of this surface nuclear magnetic resonance is we are able to also segregate the presence of water below the surface as bound and mobile. What do we mean by bound? Bound water are the water that are present in small, very minute interstices which cannot easily flow, right. When the pore size is so small, imagine clay. If clay is present below the surface of the earth, most of the water present in clay will be bound water. That means, water cannot be removed from the clay. Water from clay can be removed only by heating, right. So, that quantum of water we are able to estimate. That means, we are able to estimate not only the total porosity, but we are also estimate the volume of water that are under bound conditions, the water that are freely movable. So, if movable water is present, that is very good for us to extract, right. Such sites can be suggested for drilling a water well, right. So, how we are able to subtract or determine, separate the bound from mobile using the decay times, right. So, the relaxation time of bound water, right. That means, bound water is the water present in very tiny pores, right. When the water is present in such tiny pores, the protons that were excited takes only very little time to relax back, right. So, when if you consider my hand, please look at my hand. If this is the Earth's magnetic field, the protons in the water were initially in equilibrium with Earth's magnetic field. When we passed radio frequency through the surface coil, this made the proton to change its direction like this. When you switch off, it spins and slowly reaches the original position, right. So, this relaxation time is very, very small for the water that are in bound condition, whereas the mobile water, which are when the water can be called as mobile, when the water is present in larger pores, water can easily move through. When the water is present in fine clay, water won't be able to move through. So, the mobile water is the water that is present in the large interstices, and this water or this protons in such water takes longer time to relax back, right. So, using this relaxation time, we are able to segregate what is mobile water, what is bound or immobile water, right. Another advantage of NMR, which we will see under the NMR logging methods, right. The NMR is also able to distinguishes oil from water. How? Because of the difference in the relaxation times, right. Here too there were some difference, right. The relaxation time of immobile water, right, or bound water is quicker, it can quickly relax back, whereas the protons in mobile water takes more time to relax. Similarly, there is a time difference between water and oil in relaxation times, right. So, essentially how quickly their nuclear spins return to the original state, that means it spins and reaches the original state. So, this is the Earth's magnetic field, let us say, and this is after radio frequency, the protons change its direction here. When you switch off the application of current, it spins slowly and reaches its original. The water generally exhibits much longer relaxation time. Water takes more time to relax compared to oil, right. Hence, based on the time difference, we are able to subtract which one is oil or separate which formation has got oil, which formation has got water. How we can try to separate by analyzing the NMR spectrum, right. So, this tool is very much applicable when we are going to see borehole logging, right. In borehole logging, the same instrument is lowered in a borehole. So, we are able to pick formations that has got water, formation that has got oil or both. So, we are able to segregate. That is another greatest advantage of SNMR. So, as I told you, this is the only technique that is able to get the signal. That signal is very much depend on the presence of hydrogen or presence of fluid, whether it is water or oil, we are able to also distinguish. So, this method is so very important.